Alright, we have two more questions left in this section. Exponential growth and decay is our topic. I think we did last two questions that were about growth. Population was growing and we ended up with positive growth rate. Initial amount, positive rate, time period, growing happens. The final population was what we used in the last question. And for radioactive materials, radiate means you're giving away energy. So material becomes less and less. So radiocarbon dating is widely used in crime scene investigation, in archaeology, especially archaeological site, to measure the age of the bone, whatever belongs to how old or what period, what year that human being or animal lived. Okay, so carbon dating is a tool that uses mathematical modeling of initial amount, E raised to some change rate, times over the period of time. As you see, the rate is this time negative. That means the material is getting less and less. The carbon in the bone gets less every year, every second actually. But it's very slow process. As we found a human bone, we don't know how many years before this human lived. We are trying to date it. And what we measure is right now in that bone, only 25.5% of the original carbon supposed to be left in that bone. So there is an original quantity we don't know. Okay, it's fixed though. I think that this number is known very well. So there is an original number expected to have, and we only found 25.5% of it. Question is, how old is this sample? How many years back this guy lived? And we need to round it to the nearest year. Okay? So, why don't we take that formula and start working on it? Q of T. This is the current. Right now, you take the measurement and find how much carbon left. You put it right here. This is the reference value the bone's supposed to have many years before. Whatever that reference value is, it's not given to us either. What we know is how much carbon decays over the years. Carbon decays at this rate in bone, okay? And we are looking for time, how long passed to drop to the value of 25%. So this is our princess we are looking for, okay? This is the unknown. Alright? That means you need to know everything else as a number, or somehow you need to cancel and get rid of them in the equation. Do I know Q0 in the statement? I don't. They didn't tell me initially what's this initial starting value, amount of carbon is supposed to be in the bond. Do I know the current value? Somehow, a little partially. They say they don't say 25 pounds or grams or whatever the measure. They said 25.5% of original remain. So how can I use this fact? 25.5% of original means, change this. It's 25.5% of the carbon still remained.
0.255. Is that what we've used there?
It's what would be, I mean, you would change this into decimal if it's a rate. This is not the carbon rate is increasing or decreasing. Then I would use it here. So when the percent is given in to refer to rate, we use it here and we change decimal, but this is not the rate. This is the current amount of carbon. Like if it was 1 pound, you have now 25% of 1 pound left here. If it was 10 pounds earlier, you would have about 2.5 pounds left. So I believe this Q of t can be written in terms of Q of 0. So here is maybe the only trick this question requires. Q of t is not explicitly, numerically, completely given to us. They told us current amount is some part of original amount. How much part of that? 25.5%. 25 over 100 of original amount is left. Okay? So this is the only smart move we need to make in this equation. And then the rest is quite steady, simple. Just like earlier, we are trying to reach at t value. So you need to cancel on the left side everything and get t all by itself. I need to reach to t. And I need to get rid of q0 first. Right? Always this number is first. How do I get rid of it? Divide both sides, right? And when I do that, look what's happening. These two are canceling. And that q0 is gone. The left side is only a ratio now. 25.5 over 100. I can see from the number of zeros, it's a very slow decay. It's changing slowly. All right, next, 000, right? Okay. We need to just get rid of this base. How? As usual. I don't know how many times we did this trick, but ln natural log is required here. And of course these will cancel and this will fall to the ground. And I will have a ln of, I'm waiting for this, I don't compute this yet. Don't change into number yet, because it says do not round intermediate calculations. Don't compute this soon. Wait until the last moment. Now our t is on the ground, but it's protected by this number. You need to just wipe it off, right? By doing this. Correct? There you go. Go ahead and compute that. And see how old this bone was. We got 11,293 years. It needs the nearest years. I drop off these digits. 11,293. Looks too much. Too many years. Did I do everything right? Did I tap inside? Alright, there's no need to figure out this. Looks like a very old bone. 11,000 year old. Alright? Any questions? Alright, this looks standard. The last thing is a little bit different though. You see our equation changed a bit. The model they use, whatever the situation here is changed. Look at this. Yeah, we still have a similar phase here, right? 9.8 initial amount times the rate changing over years, but they added 1 to it and put it in the denominator of 55.3. What is this? Alright, this is more realistic approximation. Much better than regular e to the rate t1 PERT. Why? Because this is used to model Canadian population. You expect in a country population doesn't grow indefinitely to infinity. Because you don't have enough land, you don't have enough jobs, you don't have enough food to feed everybody, right? After a while, the people will migrate and populate, but after a while there is not enough space for everybody, and the population will be stabilized. You will stop populating. Okay, right? That makes sense, correct? Like, world is not going to be able to feed everybody, right? So after a while, a country's population or bacteria population, whatever population, or sheep, you're feeding sheep, maybe growing sheep, you can't take every sheep in, all right? You need to put a cap. So this model says you cannot pass 55.3 million people in this country. So they put a cap and then they let it grow as much as you can over the years. But if you want to cap, limit number of cows you have, chickens or people, you put it on the top and divide it by whatever the amount you want it to be growing, okay? How fast you want to grow it. So this is a really better approximation because we don't have always increasing populations. So what's the question here though? So they have created this model starting in what year? 1900. So they are estimating population of Canada starting 1900 with this formula. And after 300 years, you see it's not moving anymore. It's capped. And that number, I believe, is going to be 55.3. I need to figure out, though, is it really 55.3? I need to prove it mathematically. Let's read the main statement. Where is the question? As the population, blah, 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 and here is on the bottom. Let's keep this one here. You need to first understand what P0 means. Where is 0 on x-axis? Oh, right here. So they need you to find out how many people were living on Canada in year 0, which is 1900. Evaluate P0 and find out how many people were living in Canada in 1900. Can you find it? Well, from the graph, I approximated about 5 million-ish. 5 million? No, we need to give the exact number. So guess what I'm going to use? What we are going to use? How do you get the population of Canada in 1900? Year 0. Yeah. Take the formula. Here, plug in 0 and compute that thing. Okay? So I will do that right here. I just do it right on the spot. See, that's a lot easier. 0 here. I mean 0 there. Okay, what is 0 times any number? Yeah, it's going to make this entire top, this part, 0. Okay. Now, question next 2. What is e raised to power 0? .7 is like number 2.7-ish. Power 0 is 1. Okay, no matter what the base is actually, when you have a power 0, it's always 1. So this is not special for e. Any kind of base raised to power 0, as long as base is not 0, that exponential is 1. So what we have so far is this part right here. Oops. This part is 1. Okay? What is 9.8 times 1? 9.8. When I add 1 to it, it increases to 9.8 plus 1 is 10.8. Alright, at this point we need a calculator. 55.3 over 10.8 is, anyone? 8?
5.12437. It was 037, sorry.
1, do we have 1 after 1?
5.12.
2,
037.
3, 7. Let's see how much approximation they want. They just want in millions. Oh, by the way, this is in millions. So it's just 5 million then. Okay. What year was this again? The year 0 is the first sampling is taken. It's actually saying here. 0 represents 1900. Oh, it says nearest 10. Oh, yeah, I didn't see that. It says nearest 10th of a million. So we need to go one more digit. What is it? 5.1. Thanks. Alright, next, find what the population of Canada will be 30 years later, 2030. Again, don't expect to get that data from the picture.
Wouldn't that be 130 years?
Yeah, 1.130. I just ordered it now.
I'm sorry, come again?
Went from 1900 to 2030.
Oh, yeah, thank you. Yes, it is 2030, so it's 130 years. Thank you. 130 years later, 2030. Can you find it 130 roughly on the picture? Yeah, 130 is about there. 35-ish, 36, 37 maybe? I can't pinpoint it, but if I use the formula over there, I can get it, right? Q of 130, you need to go 130 as 55.3, 1 plus 9.8 e to the minus 0.02513. Times what? How many years passed? Again, 130. Alright, this is what we need to enter. Please, if you know the answer, let me know. Anyone? What's that?
40.3 million.
40.3.
Yeah.
You already reduced to the single digits. First scan, thank you. Next. Alright, how about 2070? All you need to do is 170. Try 170 here. I think it's gonna be more than 40 million. What is it? First, estimated from the picture 170, I'm expecting a little bit around 50 million something, or maybe under. So when you get a weird answer from your calculator, you can justify it from the picture. But what did you get?
48.6.
48.6, that seems reasonable, around 50. Okay, from the, now the things has changed. They're no longer giving us the year and asking us to estimate the population. This time it's backwards. They have given us the 40 million population, and they are saying which year do you think Canada will reach this amount? Hey, we have a close by estimate, right? It was 2070, 48 million. In 230, yeah, I'm expecting a near 2030 year. Well, we need to get an exact number. So guess what I'm gonna do next? This time 40 million given, 40 given, time is unknown. Alright, t is asked. You need to solve for t. Okay? So, one way to do this question is, I like cross multiplication. Multiply 1 times 55.3, set it equal to 40 times this stuff. If you like that easier. Otherwise, you can flip both sides, multiply both sides by 53 to get rid of the denominator. That works as well. I like this one, so I will multiply 40 by this. And set it into 55.3. Not only multiply, I actually want to divide this because I want to get rid of all this junk and get my t alone. So I will divide both sides by 40 actually. And even subtract 1 later. Now we will have almost there, we will get that almost alone, except you have a couple more items to drop. By the way, if you set the common denominators here, this thing is 40 over 40. 55 take away 40 is 15.33. That thing is 15.3 over 40. To subtract these two, 40 take away 55 over the denominator. Next, I will divide both sides by 9.8. Alright? And finally, we will take ln of both sides. You see, you are now in the doorstep of this tower. You need to kill this base e, and that can only be done by taking ln. ln on both sides. Alright, we have ln and e cancelled. I may have missed a digit here, please double check. By the way, this is 4 times 98 is 392 or 39.2. You can do basic calculations. As long as you're not rounding, you can multiply, divide things, okay? So it's 39.2. And the last thing we need to do is divide both sides by the rate given. So again, take this in parentheses when you are dividing, slash, put this thing into calculator, and get the year. Okay? Oh, we already have almost that thing set up. 15 point, you see, we end up getting the same ratio all the time. 15.3, 39.2, and the rate. Is my rate correct? 0.02 and 513. That's 37.4 years. Is it reasonable? Were you expecting that amount? Yeah, because 40 years you're gonna reach into in 40 years. No, 30 years, 40 million. This is not correct. It takes us 30 years to reach 40.3. So I'm expecting something less than 30 to reach 40 years, 40 million. This is too much. We messed up somewhere.
Isn't it 55.3?
double check. 15.3. 55.3, right? This top. Yeah, 55.3. To reach 40 million again, we are gonna reach it before 2030. How did I get 37? Alright, that means there is only one way to explain it. I made a mistake in somewhere here. What is 40 times 98? Seems correct. Yes.
Okay, so it's not 30 years, it's 130 years, because it's 2030, and then the whole 39.2, that should be 392. If you plug in 392, then you'd have 129, and that's like really close to 130 years, so it makes sense.
Alright, where is the mistake again?
The 39.2 under the 15.3,
Mhm.
should be 392, shouldn't it?
Yeah, of
Yes.
course.
So that decimal shouldn't be there.
Right.
And then you've been saying 30 years, that'd be from 2000, but it's from 1900. So then that would be 130.
Yeah. We just need to flip them to see. Yeah, 129 years. Let's say if it makes sense now. I said always 30, but yes, 130. Thank you. So it takes 130 years to make 40 million. 0.3. To make just 40 million, I'm expecting a little lower than 2030, and we got it now. 129. Thanks. Pass.
129.1.
Yeah, we need to round it into nearest 10, so I need to round this up to 1. Thank you.
It'd be 2029.
Yeah. Yeah. 2029. And now we don't need to worry about the decimal because we will be in that year, still that year, so finally, yes. Alright. Here's the question. This is a logic question, okay? You don't need strong math here. They are checking when t becomes an unbelievably huge number. Imagine you have a huge number here on the top. Okay? Multiply with this decimal. What is 0.02 times a huge, biggest number you can think of? It's still big, right? It's still big. So even though this is small, since t is so large and it keeps enlarging, this top is huge, infinity. When you raise e into infinity, what do you get? You have e with a huge power. Do you want to check what's going on there? I'm asking this. E with a huge exponent. Isn't e 2.7? So that means you keep multiplying 2.7 how many times? This number of times. What do you expect to get? You do this all year. 2.7 times, 2.7 times, 2.7. What do you get? What?
A very large number.
A very large number. This is a huge number in capitals. Okay? Alright, take a calculator, divide 9, now you know this thing huge in capital letters. 9.8 by the biggest number you can imagine, divided, what do you get? 9.8, about 10. 10 divided by unbelievably huge number. What do you expect to get? There are so many digits here, big digits here, you can't count. You will get 0.00000000000 indefinitely, almost zero. We call this thing limit. This number, the bigger the t gets, this is gonna be closer to zero. And eventually it will be zero if you hit infinity, which you will never. So we assume this to be zero, okay? So that's the explanation of what happens to this term eventually. It reaches to zero value, goes towards zero. This arrow means doesn't exactly become zero, but it goes towards it. Okay? All right. Now they are asking when t goes to infinity after 1900, add 1 million years, 1 billion years. What's the Canadian population is going to be? Look, from the picture, where's the picture? Here. I know it's going to be capped here indefinitely. It's never going to exceed this level. 55-ish value. Here is the second reason why it's 55-ish value. This thing, 9.8 e to the negative 0.2513 t is let's keep this t. This is the formula, right? T's. This is a negative exponent. I want to make it positive exponent. How do you make negative exponents turn into positive? This is negative. I don't like negative exponents. I will make it positive. I just put this in 1 over e, or send it under 9.8 with positive rate. All right, just a minute ago, what does this number become? Where does this go as t is huge, as t is infinity? 1 million years later, what is 9.8 over e to this number will become? 1 million or 1 billion? Where is that part? Look, isn't it the same thing? Where did this go? It went to zero. So when time passes, this part becomes zero. This guy is going to become zero then. Well, what is 1 plus 0? 1. What is 55.3 over 1? It's 55.3. So Canada, with this model, population is going to stabilize in 55.3. It will never pass as years go infinity. Okay, with this model. Of course, it's a model. It's a human-made model. So this is only an estimate. Can it pass? Yeah, of course it can pass. This is just with this model. You don't expect to pass 55.3. All right. And the picture also verifies that, right? It's going parallel to 55 level. All right, this chapter is over, guys. You are now perfectly graduated from college algebra, basically. No, it's not over. We are in the rest of the weeks. We are going to review, work on more application, real life problems, and also maybe play fun games. Okay. But I am done with the numerical part, computation part. We will just put it in the next level. We will review, experience more, practice more. Okay? Still still have more time. But why don't we do why don't we start next Friday then? Okay. So I'll let you go over the stuff.